Hey everyone, welcome back to another video about physics past papers. Today we're going to talk about the multiple choice paper 1 from the May June 2025 series. Last video was variant 1.1, this video is 1.2. So we have created a few resources which we have neatly packaged it into this grade booster pack. These are going to be very valuable for you. So let me show you what these 8 files are for now. AS Definitions and Formulae, it contains all the necessary terms, some very key revision points. This is the table for reasonable estimates, which come in paper 1 and paper 2 often. Important formulae. Then we have derivations required by the syllabus and the paper 2s often. Frequently examined questions. These are the theory questions which come in paper 2. We are working as we speak to include paper 1 questions also. A2 definitions and formulae, these again, which is very similar to the AS1 which I showed you. Key definitions, key points, and their formulae. Then we have important derivations for A2. Again, some of these are very frequently examined ones. This, for example, this one, the Kepler's third law, this comes in different forms every now and then. Frequently examined questions for A2, how we have structured this is you can see that this on the leftmost column we have syllabus points. The 2 following columns are relevant questions and the marking scheme aligned answers. The last column is the year. We're still working to get more comprehensive on that, but there are still some questions you will find that they will have a lot of years listed on the right hand side, so those will be very, very important. Moving on to the graphs, we all struggle with gravitational field and potential graphs for gravitational fields and electric fields, so we've got you covered on that front. Last but not the least, the paper 5. Students often struggle with planning question. So this contains a checklist as per the marking scheme and the examiner reports and the marking schemes, along with a few worked examples of past paper questions, October, November 2024, 5.1, 5.3, and 5.2. Although I admit this all will not fit in the space given in the exam, but still it's good enough to show you how thorough and detailed you can be, and what items to include, what items are not necessary, and how to keep it brief. All right, moving back to the question paper. Okay. What must all physical quantities have? Now, this is a very important question. Just to show you that we do have this over here in the first, okay, this one. Physical quantities, all physical quantities consist of a numerical magnitude and a unit. That means numerical magnitude means a number, a size, and a unit means something to compare against. So D right away is the correct answer. Oh, sorry. What is 0.25 kilonewtons per millimeter squared expressed in Newton per meter squared? Okay. So this is simple basic math. We need to be able to convert kilonewtons per 1 millimeter squared into equivalent form, Newton per meter squared. To go from kilonewtons to newtons, we multiply by 1000 or 10 raised to power 3. And to go from 1 millimeter squared to meter squared, you need to remember that 1 millimeter is 10 raised to power 3 meters, so 1 millimeter squared would be 10 raised to power minus 6 meters squared, so this would be 10 raised to power minus 6 meters squared. So once we take it on the numerator, this becomes 3 plus 6, 9 Newton per meter squared, and when we convert this into standard form, this will be 2.5 10 raised to power 8 Newton per meter squared. Now let's look at the options. This is incorrect, this is incorrect, this is incorrect. This should be correct, but let's count. 1, 2, 3, 4, 5, 6, 7, 8. This is correct. A student calculates the density of a solid steel cube in an experiment. The measured mass is 975, 10 grams plus minus 10 grams, and the measured level length inside 50 millimeter plus minus 1 millimeter. What is the density of the steel? Okay, so first thing you notice over here that the length is given in millimeters, but the density is given in centimeters. So if we do the calculation for density, we will have to convert this into centimeters. However, we don't really need this right now because all of these are 7.8 grams per centimeter cube. So we don't need to do the calculation for density. We just need the fractional or the percentage uncertainty for that. So for the density, we have mass per volume. Volume, this is a cube, so this would be length cubed. So for fractional or percentage, we will have mass over mass plus 3 times by sigma L over L. Fractional uncertainty is unbothered by the unit over here. So even if we go from centimeter, even if we go into centimeters or meters, the fractional uncertainty or percentage uncertainty will remain the same. So 10 gram over 975 plus 3 times by 1 over 50, and then we will multiply this all by 100 to find the percentage. So 10 divided by 975 plus 3 divided by 50, then times by 100. This is 7.025. This is going to be B. Oh, sorry, my bad. Okay. The time period T of a pendulum is given by formula, where L is the length of the pendulum, G is the acceleration of the free fall. Equation is homogeneous. That means the units on the left-hand side match the units on the right-hand side. What is the value of N? So basically, this is just simple math. Again, we have to figure out what is the index over here. What is the value of the index over here? So 2 pi is basically a constant, so it has no units. So the unit for T time period is seconds, unit for length is in meters, unit for G, which is the acceleration of free fall, is meter per second squared. So that means that the L per G is meter over meter per second squared, which if you realize cancels out the meters, and we are just left with second squared. So L over G raised to power n would be S to n. Now this is T, the units for T equal to the units for L over G raised to power n. So S1, which is this here, equals to S2n. So bases are the same. We equate the powers. So 2n is equal to 1, n would be 1 over 2. C. Okay, all right. Radio waves can be used to measure the distance between the Earth and the planet Jupiter. Pulse of radio waves is emitted from the surface of the Earth. Pulse reflects from the surface of the Jupiter and is detected again on Earth. Time between emitting and receiving the pulse is 3960. So basically what's happening over here is that this is your Earth, this is your Jupiter. Oh, sorry, my bad. There is a pulse going in this direction and a pulse coming back in this direction. I don't know what's wrong with this. So the 3960 basically is going forward and backwards. So if we just want the one-sided distance, we will have to divide this time by 2. And what speed can we use? Since this is radio waves, this is going to be speed of light. So distance is equal to Vt, speed 310 raised to power 8 meter per second. But over here in the options, it's used kilometers. So instead of 10 raised to power 8, we will use 10 raised to power 5. Simple division by 10 raised to power 3. 5 kilometers per second times by 3,960 divided by 2. So 3 times by 3960 divided by 2, 10 raised to power 5. This is 5.94, 1, 2, and 6, 8. So A is the answer. The graph shows the variation with time of the velocity of the car. Okay, let's first examine this. So constant rate of velocity increase, this is positive acceleration. Velocity constant in this part over here, so acceleration is 0. Velocity decreasing uniformly, so negative acceleration or deceleration. Okay, the car accelerates for 2 seconds, then stops for 4 seconds, then reverses. So velocity being constant, positive, 0, and negative does not mean the same thing as acceleration being positive, 0, and negative. Acceleration being negative just simply means that it's decelerating. Acceleration being 0 just simply means that the velocity is constant. So this is cancelled right away. Car accelerates at 12 meters per second squared for 2 seconds, which is not correct, but because in this part over here from 0 to 2, v minus u over t is 12 minus 0 over 2, which is 6 meters per second squared. So this is cancelled. The car travels a distance of 36 meters in the first 4 seconds, and the next option is 48 meters in the last 4 seconds. Okay, so we can test both of them side by side. In the first 4 seconds is this. That means this includes this triangle and this small rectangle. In the last 4 seconds would be this. So let's calculate both of them side by side. Let's change let's use different colors for them so we don't get confused. Okay, never mind. So the first one, the first 4 seconds is first is a triangle times by 2 times by 12 plus 2 times by 12. So this becomes 12 plus 24, which would be 36. C appears to be correct, but just to you, although this is going to be the correct, but let's check this one also. Half times by 4 times by 12. So this is 24, not 48. So C is the correct answer. Okay. A solid object of mass 1 kg falls vertically downwards in a vacuum. When the speed of the object is 60 meters per second, an additional constant force of 50 Newton suddenly starts to act vertically upwards on the object. What is the speed of the object? 2 seconds after the additional force starts to act. Okay, so basically what's happening is this is the object which has the weight mg, since m is 1, so we are just going to write g. The force now acts 50 newtons upwards. So we have sigma f is equal to ma, second law of motion basically. So what's happening is that sum of force is g minus 50 because this is the direction it is still going. M is 1. Acceleration, we can do v minus u because we're talking about change in velocity. This is u now because this is the initial velocity where this begins to act. So v minus u, over, we can actually, v minus 60 meters per second divided by time, which is 2 seconds. So cross multiplication, 2 goes on this side. This becomes 2g minus 100 equals to v minus 60. So v would be 2g minus 100 plus 60 minus 40. So let's figure out what this means. 2 times by 9.81 minus 40. This is minus 20.38. This is velocity. So this would mean that the velocity now is upwards because as you can see, this is significantly higher. So Since previously it was going down, then it turned back and started going upwards. So velocity going negative. In this particular instance, we took negative downwards as positive, sorry. So negative would mean going upwards now. So speed now, not the velocity, speed is now 20 meters per second. Okay. A stone is thrown upwards and follows a curved path. Air resistance is negligible. Why does the path have this shape? Stone has a constant horizontal acceleration and constant vertical velocity. Now, what it does have is, let's write over here. So it has constant vertical velocity, oh sorry, acceleration, my bad, downwards, and constant horizontal velocity to the right. So this one cancel. The stone has constant horizontal velocity and constant acceleration. This is exactly what we just wrote. So B is the right answer. A rocket engine ejects 90 kilograms of exhaust gas per second. Okay, this is interesting. 90 kilograms of exhaust gas per second at a velocity of 190 meters per second relative to the rocket. What is the force acting on the rocket due to ejected gas? Okay, so to show this, so there are three concepts at play over here. Newton's third law and second law also, basically. Side by side conservation of momentum. So what is happening over here, that as the rocket expels gases, it exerts downward force on the atmosphere, air, and as a result, the air or the gases actually exert an upward force, which we call thrust upwards. So the force on the gases, force the gases exert on the rocket is upwards thrust. Now, we know that the force is rate of change of momentum. But we are more accustomed to using constant mass and a change in velocity over time. However, in this case, there's a change in mass happening per unit time and a constant velocity. So this will not be applied because the mass is not constant. Instead, mass is changing with time and velocity is constant. So mass changing with time, they have given us the value 90 and velocity is 190. So 90 and 190. So 90, 190, 17,000. So 17,000 is speed. That's it. Simple. So conservation of momentum over here means that the velocity or the momentum of the gases expelled will be balanced by the momentum of the rocket, because before the expulsion the total momentum is 0. So they are going in opposite ways with opposite momentum. Second law is applied over here. Third law, as we have seen, that the force on the gases, force on the rocket are opposite and acting on different bodies. Now, okay, which statement does not describe an elastic collision between two objects? Elastic collision means that the kinetic energy and momentum are conserved. Let's see. Relative speed of the approach of the two objects equals the relative speed of separation. This does describe the elastic collision, although there's a minus sign somewhere, but the total kinetic energy of the objects is conserved. This is elastic. total kinetic energy of the objects is reduced. No, this is not correct because this would be inelastic. A cyclist is riding at a constant speed on a level road. According to Newton's third law of motion, what is equal and opposite to the backward push of the back wheel on the road? So basically, this is what we're talking about. What is the opposite to backward push of the back wheel? So this is the backward push. Let's call it B for now. This is, as the word suggests, on the road. The Newton's third law of pair would be on the wheel because these pair of forces act on different bodies. So first off, we need to see which one is acting on the wheel. So there will be a forward push on the wheel. Let's call it this forward push on the wheel. So force exerted by the cyclist on the pedals, no. Force forward push up off the road on the back wheel. Yes, exactly. That's exactly what we were talking about. Right, okay. A stone is released from rest and falls a long distance in air. Which graph would show the variation with time t of the acceleration of the stone? So acceleration is going to be the same constant. So 12 is, oh, long distance in air. Okay, so they did not say that the air resistance is negligible. So it will achieve terminal velocity if this is the case. So its acceleration would reduce. So D would be the correct answer. Okay. An empty cart is moving along a horizontal track at a constant velocity. Resistive forces acting on the cart are negligible. Heavy rock is dropped vertically into the cart. The cart continues to move horizontally with the rock inside. How does the momentum and kinetic energy of the cart with the rock inside compare with the momentum and kinetic energy of the empty cart? So with the description, it's not dropped from a very uh, height. It's dropped such as it doesn't cause any wobbling or disturbance of on the cart. So it's just gently placed on it, sort of like that. So suddenly, so it's going, the cart is going, suddenly the mass is increased. So because of that, the momentum will be the same. So the momentum will be the same. So as you can see, smaller momentum, A and B, we can, eliminate them. Now, the question about the kinetic energy. So momentum, let's say before, is after. Momentum after. Which would mean that the square of the momentum will also be the same. Correct? Okay. Then we have the question of mass. So mass before is less than the mass after. And let's call it initial, final. Be that. Why am I going to that? So initial is less than the final. So this would mean that the reciprocal 1 over mass initial would be greater than the 1 of the mass final. So P initial squared divided by mass initial would be greater than PF whole squared mass final. Now, as you can see, this is the definition of kinetic energy with respect to momentum. So if you multiply 2 and 2 over here, it keeps the inequality balanced. But for kinetic energy, momentum and mass are the deciding factors over here. But as you can see, the EK initial is greater than the EK final, which means that after that, it will have a smaller kinetic energy. C would be the right answer. A wooden block is held stationary in a container of water using a string that is attached to both the wooden block and the bottom container. The wooden block has a mass m and a volume v. The water has density rho. The acceleration of free fall is g. What is the magnitude of force acting on the block due to the tension in the string? Okay, so tension is pulling this downwards, and there's a weight also acting mg. Upthrust, which is going to be rho gv, because this is entirely submerged, so rho gv. So rho gv is equal to tension plus mg. So tension would be rho gv minus mg. So D would be the right answer. A square shop sign of uniform density has a mass 2.4 kgs and a sides of length 0.86 meters. Okay. Uniform density means that its center of gravity is at the exact center. Sign is supported by a hinge along its top edge. There's a friction in the hinge so that the sign hangs from it in equilibrium at an angle of 15 degrees to the vertical. What is the moment about the hinge of the weight of the sign? So since this is in equilibrium, momentum counterclockwise will be equal to sum of momentum clockwise. Weight is acting downwards at this point over here, halfway between this. So this would be 0.86 divided by 2. This would be 43. Sorry, 0.43. So we also need to know the perpendicular distance. So perpendicular distance is going to be this one from this. So perpendicular distance is this one, but the line of action of force has to be perpendicular also. So we need to resolve this force over here. The angle is already given to us, so this is the same force over here. So this is going to be mg sine 15. So mg sine 15 times by 0.43 equals to friction. Actually, oh wait, sorry. What is the moment about the hinge of the weight of the sign? Actually, this is it. We don't need to do anything, right? Yeah, okay, we don't need to do anything. So 2.4 times by 9.81 times by sine of 15 times by 0.43. This is 2.6, and A being the right. A being the right answer. That's it. Okay. A block is submerged vertically in a liquid. 4 diagrams show the block viewed from the side. Which diagram shows to scale the forces exerted on equal areas of the block by the liquid? Okay, so this is the side view now. And as you can see, there's a difference in arrows, which means that the longer arrows means a higher force, or sorry, a larger force. So we know that the pressure rho gh increases with depth. So that means as the depth increases, the pressure will increase, which would mean that pressure times by area, which is force will also increase. So force at the top, force at the bottom, pressure at the bottom will be high. That means force at the bottom will be higher. As you can see, the force is getting larger as we go downwards. This seems to be correct. But let's see the other options also. This would be incorrect because it does not take into account the forces on the side. this is similar to A, but they're assuming over here that there's a very small force over here, which does not make any sense because at this level, this is the amount of force. So this would be at least the same length. So this would not be correct. They have the same length over here, but the sides have the same amount of force, which is incorrect because as we go downwards, the size of the force should increase. So A seems to be the right answer. Okay, the diagram shows a couple. How is the torque of the couple calculated? We already know that the force times by perpendicular distance between the forces, whatever this D is. Perpendicular distance between the forces, magnitude of the one of the forces, B, right away, that is correct. A ball of mass 1.2 kg travels horizontally at a speed of 3 meters per second. Ball hits a cushion and comes to rest over horizontal distance of 0.02 meters. What is the work done by the cushion on the ball to bring the ball to rest? Okay, so work done by the cushion would be the change in kinetic energy, basically. So half m v squared minus u squared. Since it is actually stopping, you can actually also swap it with u squared minus v squared also, because v is now 0, so absolutely fine either way. So half, mass is 1.2, speed was 3 squared minus 0 squared, so this is 1.2 divided by 2 is 0.6 times by 9, so I think this would be 5.4, but let's not trust me. 5.4, so 18 is C. A box of mass 4.9 kgs is pushed at a constant velocity from point P at the bottom of the inclined plane to point Q at the top. Box is pushed by a force of 64 newtons parallel to the slope. Slope is inclined at an angle 20 degrees to the horizontal, and the box moves through a vertical height of 5.8 meters. What is the work done against the frictional force acting on the block between P and Q? Okay, so constant velocity means that there is no acceleration. So, which would mean that if the frictional force weren't present, the change in kinetic energy would be equal to the change in the mgh. But change in kinetic energy is 0 because it's moving at constant velocity. So change in kinetic energy is 0. Furthermore, that means that the work done by the 64 Newton force is going to balance out or is going to be equal to the change in potential energy and the work done against the friction force. So work done by 64 Newton force, we'll just call that force. We'll just call it 64, work done by 64 Newton, minus the work done against friction is equal to the change in potential energy. So this means that the work done against friction would be the work done by 64 Newton force minus the change in potential energy. Now, to figure out the work done by 64, we have to find out this distance, not just the vertical distance because it's moving, there's a component horizontally also. So if we can figure out the hypotenuse, so we know that the sine of 20 is equal to 5.8 divided by PQ. So PQ would be 5.8 divided by sine of 20. So 5 divided by sine of 20. So this is 16.95. So work done by this is 64 times by 16.96, let's call it, minus mgh. M is 4.9 times by 9.81 times by 5.8. So 64 times by answer minus 4.9 times by 9.81 times by 5.8. This is 806, and this is going to be 810 in two significant figures. Right, okay. Moving on. Which expression gives the efficiency of the system, useful power output, total energy input, or energy? That's it, simple. Okay. A student has a copper wire and a steel wire with equal lengths and cross-sectional areas. Student hangs identical loads on two wires. Extensions of the two wires are different. The student calculates stress, strain, and Young modulus of each wire. Which row identifies with the calculated values that are equal for both wires? So if there are equal cross-sectional area, so stress is force over area, and it is also hanging the identical load. So this means that the stress would be the same. Strain is the extension over original length. Extensions are different, so extensions will be different. Young modulus is stress over strain, since if strains are different, then Young modulus will be different also. So only stress would be the same. So 21, it's just A. Okay. Two springs, X and Y, stretch elastically. The graph shows the variation with extension X of the force applied on each spring. Which statement is correct? Okay, when each spring is given the same extension, the energy stored in Y is 4 times the energy stored in X. Okay, so this is about the energy, so we need to know the energy stored in the same extension or the same force. So we need to calculate some metrics over here. So, right. If they're given the same extension, so this means that if we do this over 10, so this would continue going double. That means this would going in the same path. So this would go over 160. Sorry, 160. So all right, okay. So the energy EP half Fx, half times by 20 times by 10, and half times by 160 times by 10. So this is 100, and this is 800. So if they're given the same extension, spring Y will store 8 times more energy as that. So B would be the correct answer. Which phrase describes the strain at the elastic limit on a stress strain graph? The maximum strain below which Hooke's law is obeyed. Stress strain graph. Okay. Stress strain graph, the straight part is where we use to find out the Young's modulus. The maximum strain below which the deformation is elastic. The minimum strain which Hooke's law is above which Hooke's law is obeyed. Minimum strain above which deformation is plastic. This is correct. So Hooke's law is from the force extension graph. When you have stress strain graph, the gradient is actually Young's modulus. So straight line would indicate the Young's modulus, not the Hooke's law. So 23 is D. A teacher removes the turntable from microwave oven and places a bar of chocolate in the oven. She then switches the oven on for a short time. The stationary wave is formed in the oven. When the chocolate is removed, teacher observes that there are two small sections of the melted chocolate, 6 centimeters apart, with unmelted chocolate between them. Each section of the melted chocolate is located at an antinote. So these are the melted chocolates. Assume that the speed of the microwaves is this. What is the frequency of the microwaves emitted in the oven? Okay. So this is an antinode, this is an antinode. So this length over here, antinode to antinode, we know the distance between antinode to antinode is lambda by 2. So this length, lambda by 2, is equal to 6, which means that lambda is 12 meters, or centimeters, sorry, or 0.12 meters. Now we need the frequency. So frequency is V over lambda. V is 3 10 raised to power 8 divided by 0.12. So 3 divided by 0.12 times by 10 raised to power, oh no, sorry, wait. 3 10 raised to power 8 divided by 0.12. This is 2.5 10 raised to power 9. This is the gigahertz. A sound wave travels from left to right. The graph shows the variation of the displacement to the right of the particles in the sound wave with the distance at one instant. Which letter represents the center of a compression? The center of a compression would be where there is zero displacement happening. Center of a compression. So displacement, this would be B. Why? So let's see that basically. So A represents farthest away. As we come close, we come closer a little bit. B is right in the middle, and then we start increasing the distance again, and then C would be the farthest distance again. So B is the correct one. A buzzer emitting the sound of frequency 846 Hertz is attached to a string and rotated in a horizontal circle. Linear speed of the buzzer is 25 meters per second. The speed of the sound is 340 meters per second. What is the maximum frequency heard by the observer? So observed frequency is V over V plus Vs F. V is the speed of the wave, Vs is the object's speed, that means speed of the object relative to the observer. So maximum frequency will be where it's coming towards this. So sorry, this will we will use a -1 because the maximum will be increased when you reduce the denominator. So when it is coming towards it, so negative sign will be used over here. So speed is 340 minus 25 times by 846. So we have 340 divided by 340 minus 25 times by 846, 913. So 26 is D. Vertically polarized light of intensity I naught is incident normally on a polarizing filter. Transmission axis of a filter is at an angle theta to the plane of polarization of the light. The intensity of the light after passing through the filter is I naught over 3. What is the theta? Okay, so we know that in the Malus law, I equals to I naught cos squared theta. So I equals to I naught cos squared theta. So I is now I naught over 3 and I naught cos squared 3 theta, sorry. So I naught gets cancelled. So this means that cos of theta would be plus minus root 1/3. So we just need to figure out what is the cos inverse of 1/3. Square root of 1/3, sorry. 1 divided by 3. So this is 54.7. So this is B. Which statement compares the behavior of transverse and longitudinal waves? Only the transverse can be polarized. This is the answer, 28D. Okay. A student uses a diffraction grating to determine the wavelength of the visible light from a source. Diffraction grating has 300 lines per millimeter. Student measures the angle of each order of intensity maxima. Graph of n against sine theta is plotted. The line of best fit for the plotted points is shown and has a gradient g. Which expression represents the wavelength in meters of the visible light in terms of g? Okay, so we have n lambda is equal to d sine theta. D is in 1 millimeter, you have 300 lines. So this would be 1 divided by 300 times by 10 raised to power minus 3, sorry. So this is, if we convert this into standard form, my bad, 3.3 10 raised to power minus 6. So this is the x-axis and this is the y-axis. So n equals to d over n sine theta. Sorry, lambda, my bad, sine theta. So d is 3.3 10 raised to power minus 6, and lambda, they've given us lambda? No, they haven't given us lambda. So this is the sine theta. Okay, so this is our gradient. So wavelength, so G is equal to basically this thing. So lambda would be 3.310 raised to power minus 6 divided by G. C is the right answer. Simple rearranging of the formula. Two waves meet. What is not a necessary condition for the waves to produce a stationary wave? They must be of the same type. It is a necessary condition. They must have the same period. That is a necessary condition. They must have the same wavelength. They must travel in the same direction. This is not necessary because they must travel in the opposite directions. Light of a single wavelength is incident normally on a double slit. Interference fringes are observed on a screen. Distance of the double slit to the screen is 0.6. This is D. Fringe separation is this is X. The distance from the double slit to the screen increases by 0.9 meters. What is the new fringe separation? So remember the formula over here, we have lambda is equal to AX over D. This is also given in the formula booklet. So lambda is constant. The items that are constant is lambda and slit width. So this means that X is directly proportional to D. Or basically you could say that X over D is constant. So what happens is that Previously, you have D 0.60, separation is 1.8, 10 raised to power minus 3. Now we are increasing by 0.90, so this becomes 1.5. And now we need to find out what the new string separation is. So 1.5 divided by 0.6 times by 1.8 times by 10 raised to power minus 3. This is 4.5, 10 raised to power minus 3, which is 4.5 millimeters, 4.5 C. A wire is made from a metal of constant resistivity. There is a constant current in the wire. Which statement about potential difference across the wire is correct? It is directly proportional to the length of the wire. It is inversely proportional to the length of the wire. Okay, so we know that the resistance is proportional to the length and inversely proportional to the cross-sectional area. So potential difference, which is VIR, and they have said that the current is constant, so V would be directly proportional to the resistance. In short, we would, since resistance is proportional to length and inversely proportional to area, so it would apply the same relationship or similar relationship to the potential difference also. So it is directly proportional to the length of the wire and inversely proportional to the cross-sectional area, or the square inversely proportional to the square of the diameter, not just diameter. The IV characteristics of three electrical components are shown. Which components obeys Ohm's law? Ohm's law is V is equal to IR, or I equals to V over R, where 1 over R is the gradient. Oh, sorry, no. Is the gradient. So this must also mean that this is sort of like y is equal to mx type situation where the y-intercept is 0. So it should always pass through 0. This is the ohmic conductor's graph. So there is only one. A resistor of resistance 200 ohm is connected to a supply that has potential difference of 4 volts. How many electrons enter the resistor in 4 seconds? So first off, we need to find out the current. So current is equal to V over R, 4 divided by 200. That is 2 10 raised to power minus 2, or 0.02 amperes. Now we need the how many electrons. So I is equal to, we know I is Q over T. So in 1 second, we have the charge flowing. So in 1 second, we have 0.02 coulombs, right? So in 4 seconds, you will have 0.02 times by 4, which is 0.08 coulombs. Now we need to convert this into number of electrons. We know that charge is quantized, so 0.08 coulombs divided by 1.6, 10 raised to power minus 19 fundamental charge. So this would be 0.08 divided by 1.6, 10 raised to power 19. This is 5, 10 raised to power 17. So C. The diagram shows a cell of internal resistance 1R connected to a variable resistor. When the variable resistor has an initial resistance of 2R, the current in the cell is I1, and the terminal potential difference across the cell is V1. The variable resistor is now adjusted to a new resistance of 4.0R. What is the new current in the cell and the new potential difference across the cell? Okay, so again, this is also written in the definitions and formulae booklet that the terminal PD is equal to the EMF minus the lost volts. Lost volts actually come from the internal resistance. So if in the first case you have V1, terminal potential difference, EMF remains the same, constant. Lost volts is 1R times by current, I, let's call it I1, R, and this is equal to terminal potential difference. This would be equal to the potential difference across this. This would be equal to I1, and this is previously 2R. So if we rearrange this, E would be equal to I1 R plus 2R, which would be 3R. So I1 would be equal to E over 3R. Let's just stick to this first now, and then we'll see what we have. This is I1. Now we have 4 times by that. 4 times by that. So E remains the same. So V2 is now E minus I2R. The internal resistance remains the same, but terminal potential difference is now I2 times by 4R. So again, when we take it on the other side, I2R plus 4I2R, we get 5 I2R equals to E. So I2 will be equal to E over 5R. So now we need to see what is the relationship between these two. And then again, the V2 we will also need to consider. So I2 ratio I1 we need to see. So E over 5R, E over 3R. So E over R gets cancelled, cross multiply, it's 3 ratio 5. So 3 ratio 5, 3 divided by 5 is 0.6. So I2 is actually 0.6 times by I1. Or if you are forgotten the basic math, this is like this, 3 by 5. Okay, so that means that these two are cancelled right away. Now we need the potential difference. Terminal potential difference is this thing, 4I2R. So this would be 4 times by I2 R. I2 is now 0.6 I1 R. We need to figure out what is R, I1R. So I1R is E over 3. No. We need to figure out what was this over here, I1R. So we need this. Okay, sorry, my bad. We need to consider these two. So if V1 is equal to I1, or sorry, 2 times by I1R, now we have V2 4 times by I2R. So 4 times by I2 is now 0.6 I1 R. So 4 times by 0.6 is 2.4. So 2.4 I1 R. So when you do V2 ratio V1, you have 2.4 I1R ratio 2 I1R. I1R gets cancelled. Divide by 2 on both sides. You get 1.2 ratio 1. What does this further mean? That V2 over V1 is equal to 1.2. So V2 is 1.2 times by V. So this is going to be D. Right, okay, moving on. The diagram shows 4 terminal box connected to a battery and 2 ammeters. The current in the 2 ammeters are identical. Which circuit within the box gives this result? Okay, let's see. There's only one way this can be true, if they are in series with each other. So there has to be some sort of series uh, relationship between this ammeter and this ammeter. So we just need to see where is this happening. So no. So some kind of series relationship over here, some kind of series. I think D is the only thing. So if you have this over here and simple line over here, so there is only one flow of current over here. So one loop over here. So D would be the correct answer. Each of the Kirchhoff's two laws presumes some quantity is conserved, which row states first law and states and names the quantity that is conserved. This is listed in this one also. Second law is based on conservation of energy. First law is based on conservation of charge. So going back, energy get cancelled. Algebraic sum of currents at a junction is 0. This is the only thing that is correct. Two neutral atoms are isotopes of the same element. They are isotopes of the same element. That means same proton number, but different neutron numbers or nucleon numbers. Either way, sorry, nucleon numbers. Okay, they have different number of neutrons and a different number of electrons. No, electrons would be the same. They have different number of neutrons, but same number of protons. This is correct. What is the composition of a meson? It has a quark and an antiquark. So one quark and antiquark, straight away, simple answer. A nucleus of carbon-11 contains 6 protons and 5 neutrons. The nucleus carbon-11 decays by beta plus emission. What is the total number of up and down quarks in the product of the decay of the decay of this nucleus? What is the total number? Okay. So what happens in beta plus is that a proton decays into a neutron and a neutrino, electron, neutrino, and this beta plus particle along with energy. So one up quark converts into a down quark. Antineutrino is already a lepton. A neutrino is already a lepton, not a quark. And this is positron, also a lepton. So it has 6 protons. Now one up is 1 proton. In 1 proton you have up, down. That means 2 ups in one. So 6 protons will have 12 ups. Along with neutrinos, neutrinos have one up, basically it's one down, down. So 5 times by u, that would be u. So this means before it's 17 ups. This is not u atomic mass unit, this is up quark. And now, since one proton has decayed, so this means that in the product, one up has been converted to one down. So this means that they're going to be 16 up now. So I think there's only no, one option that is relevant. B. So total there were 17 up quarks. One up converts to one down quark, so that means one is subtracted, so 16 up quarks. And that's about the end of this paper. If you feel that I made a mistake somewhere, or if you feel that I wasn't able to explain a certain question properly, do reach out in the comments. I would love to hear your feedback. And do check out that great booster pack on our Patreon. This is going to be very valuable. I'll give the link in the description. And hopefully we'll see you in the next video. Bye bye.